The topic I am talking today is using the Angstrom method to measure the effective thermal diffusion conductivity of the vapor chamber. Being a professor for 35 years at the National Tsinghua University in Taiwan, now I am acting as the CTO of the T-Global Technology Company. T-Global Technology Company founded in 2003. The company's partners of the whole world are more than 2,500. T-Global Technology Company does the full range of the heat dissipated products, such as the TIM, which include the thermal grease, thermal pad, and the PCM, etc. Recently, vapor chamber and other heat dissipated devices are also developed as well. In general, the thermal conductivity K values of the Zx of the material is measured by the instrument for pure substance such as the pure copper, pure alumina, or homogeneous substances such as the thermal pad or thermal grease. It is of course no problem to measure the K values by Fourier's law. The test method widely applied by TIM manufacturer is named D5470. However, in the case of the heat dissipate device such as the heat pipe, vapor chamber, or fragile materials such as graphite sheet or graphene sheet, or when the heating area and the heat dissipation area are different, thermal diffusions would occur. In this condition, the K values measured by D5470 is not right. This topic will introduce how to quickly and accurately measure the thermal diffusivity of non-uniform materials such as the heat pipe, vapor chamber, or fragile materials such as the graphite sheet, graphene sheet, etc. In addition, if the density and the specific heat of the material be measured, then the effective thermal diffusion K effective values of the material would be obtained as well. When the CPU cooler is attached tightly to the CPU, the heat transfer from the CPU to the heat sink, and finally heat is dissipated by fan force convection. Traditionally, the CPU cooler includes a fan and a heat sink. But more strictly speaking, it should include a very good TIM material between the bottom of the heat sink and the CPU surface as shown in figure 1. But why does TIM need to be added between the heat sink and the CPU? The reason is that the surface of the heat sink or the CPU surface seems supposed to be smooth and flat, but actually the surface is bumping holes that is invisible to the naked eye. Therefore, when the heat sink is attached to the CPU, there are still many voids. When these holes are filled with still air, the still air will be a heat insulator because its lowest thermal conductivity K is 0.024. Therefore, a thermal interfacial material with high thermal conductivity is needed to fill these voids instead of the still air. TIM material is a very important part of the heat dissipation field. So how to measure the thermal conductivity K values of the TIM is very important. In general, when we're talking about the K values measurement of the TIM, we are talking about the ASTM D5470. The measuring thickness is in the range of the 0.02 to 10 millimeter. D5470 is based on Fourier's law. The sample of the thermal interfacial material having a diameter of about 20 millimeter is passing through a stable heat source to measure the surface temperature of the material. That is, under the same heating area and the heat dissipation area, the K values of the TIM material is obtained without any thermal diffusion conditions. Diffusion is useful for K measurement of pure materials such as the copper, alumina, or homogeneous materials such as TIM, which is in the Z directions. However, when a two-way exposed thermal conductor such as the heat pipe vapor chamber or the brittle materials such as the graphite sheet or graphene sheet applied on thermal diffusion device, in this case, the K values of the heat dissipated device cannot be obtained by using simple Fourier's law. Why cannot we use Fourier's law to measure the thermal conductivity? Because the object of the heat pipe, vapor chamber, or graphite or graphene sheet are used for the thermal diffusions. The thermal diffusions, in other words, the heat source area is different from the area of the condenser, and generally the heat source area is much smaller compared with the condenser area. Therefore, in here, we are going to give a detailed description of how to use Angstrom method to measure the effective thermal diffusion K values of the vapor chamber. The thermal conductivity K values represent the material is a good heat conductor or not. The larger values of the K represent the higher the values of the power watts that the object can transmit per unit temperature Celsius degree at a distance of 1 meter. In other words, the temperature gradients at the same length is smaller, hence temperature transfer speed is faster. However, the time required to reach the final temperature cannot be determined. Thermal diffusivity alpha represents the area where the heat can spread per unit time and the same power. Therefore, the larger alpha value, the larger the partial temperature with respect to time value, it is also implying the temperature change rate of the unit time in the object is larger. So the time required to reach the final temperature of the substance is shorter. The thermal conductivity K values is the most direct description of the thermal conduction abilities of the material. Most of it is measured by Fourier's theorem. However, this method is feasible for solid heat conduction and makes sense under the condition that the heating area must be the same as the heat dissipation area. But for devices such as the heat pipe, which utilize the latent heat of the working fluid and the heated convection of the working fluid to make the heat transport purpose as shown in Figure 2a, or the brittle materials such as the graphene sheet and the graphite sheet as shown in Figure 2b and the Figure 2c. Or when the heating area and the heat dissipation area are different, there must exist a heat diffusion process as shown in Figure 3. In these situations, to measure K values by D5417 method is not feasible. To measure the thermal diffusion conductivity K of this specific material, the Angstrom theory provides a good measuring method. Angstrom theory is basically using a periodical heating patterns into a one-dimensional long strip of the test sample. The theoretical diagram of the measurement is shown in Figure 4a. When applying a periodical sine wave heating at point Tc, this sine wave is thus propagating from T sub c to the second point T sub x. The governing equation of the Angstrom's one-dimensional control volume can express of equation 1. After the calculations is simplified by separation variable method, the thermal diffusivity of the object to be tested can be calculated by the heat transfer formula equation 4. Figure 4b is the schematic diagram of the temperature trend distributions according to Angstrom theory by measuring the temperature amplitude T sub c and the T sub x at both temperature points, and the delta T between T sub c and T sub x peak. and the distance L sub m between T sub C and T sub X, the thermal diffusivity alpha of the one-dimensional object to be tested is thus be able to infer. Figure 5 shows the concept of the thermal diffusivity measurement device. The heat source of the heating power is input with the sine wave, and the test strip is placed on the top of the heat cover block, and the two temperature sensors T sub C and T sub X are respectively installed on the sample strip to be tested. When the sine wave of heating power is transmitted from T sub C to T sub X and the temperature change is recorded, the red curve and the blue curve in figure 4b can be obtained after a periodical time to be thermal equivalent. The heating fixture is a TEC chip. The core side of the TEC is combined with a heat sink to remove heat. The thermal diffusivity measuring instrument, namely TDMI, is mainly composed of the three parts. The heating fixture is the TEC chip as shown in figure 6. The thermal diffusivity measuring platform is shown in figure 7. And the power supply are as shown in figure 8. The program controls the output at the sine wave heating power required for experimental to the tested sample, except the T sub C and the T sub X. Another temperature sensor T sub Y can be adjusted to measure additional temperature points. Of interest, the test sample gantry support frame is used to avoid the bending of the test strip. For example, graphite sheet may be bending due to gravity. In order to verify the accuracy of the instrument, calibration experiment must be carried out. A pure substance metal such as the copper, tin, lead, and aluminum 6061 was selected as the standard test sample. The typical thermal diffusivity values of this metal can be found in the textbooks, networks, or literature. The data measurement is in the form of a full blind test. First, the repeatability of the experimental data must be precise and determined. The repeatability error shown as in equation 5 refer to the same persons repeating several times measuring during the experimental, comparing each measure result with the total average. The relative error is, of course, the lower the better. The accurate relative error refers to the relative error between the tested results and the standard values of the golden sample expressed by equation 6. When extracting experimental data, people need to know first whether the extraction of the various parameters in thermal diffusivity is rationality or not. Taking the thermal diffusivity of pure copper as 1.170 as an example, the four parameters of the thermal diffusivity according to equation 4 are L sub m, delta T, M, and N. Therefore, it is very important to determine whether these four values are within a reasonable range. The so-called reasonable range must meet the following three conditions. First, M is equal or larger than 2 Celsius degree. Second, N is larger or equal to 2 Celsius degree. Third, delta T delay time is larger or equal 5 seconds. The reason why M and N must be greater than 2 degrees C is that the temperature accuracy of a thermocouple is plus and minus 1 degree C. So 2 degrees C is taken as a minimum identification degree. If the measurement time is too short, the error rate is higher. Therefore, the measuring time taken at least 5 seconds. Table 1 is the tri-calculations table of pure material coupled thermal diffusivity in different measuring distance, LM, and M, and delta T is less than 4 seconds. The trial results showing when delta T is less than or equal to 4 seconds, all the N values are less than 2 degrees C, and all the data are not codified. Table 2 is the same in Table 1, but the delta T delay time is larger or equal to 5 seconds. The method is to select the different measuring distance, LM, as 3, 5, 7 cm, while M amplitude at 5, 10, or 15 Celsius degree. By knowing LM and M values and N values can be calculated by equation 4. If N is less than 2 degrees C, it is not meet the request and means the assumptions LM and M values are not suitable. On the contrary, if N is larger or equal to 2 degrees C, it means the assumptions values of LM and M are okay. The result is showing no matter what the values of the delta T or M are. As long as the measuring distance LM is equal to 3 cm, the M values passing all the requirements. When LM is 5 cm or 7 cm, some M values are not meet the requirement at the delta T is less than 10 seconds. So the best choice is LM is equal to 3 cm and the delta T is larger than 5 seconds. Figure 11 is the measurement result of the diffusivity of different measurement distance LM. There are 3 kinds of the copper test pieces with different thickness to width ratios, and the RBUS copper reference is the standard thermal diffusivity values of the copper test sample, green dot line. The experimental is measure the thermal diffusivity by different measuring distance. Figure 11 showing that the relative errors was relative close and small when LM is equal to 3 cm. At other distance, some of the test pieces having an increased error. Therefore, the conclusion of the experimenter is that it will be best when the measurement distance is equal to 3 cm. Angstrom the method was originally only applied to the one-dimensional test sample strip, and its shape is a long and thin test pieces, as shown in Figure 12. Figure 13 is the schematic diagram of the two-dimensional test sample. To simplify the model of the 2D thermal diffusions, we combine the relationship between the vapor chamber length and its thickness into one parameter, tau, namely the aspect ratio of vapor chamber. The aspect ratio of the vapor chamber is defined as the ratio of the thickness to the length. Furthermore, we use the different aspect ratio as the calculations benchmark for the 2D vapor chamber, and based on this ratio change, we further divided different zones. There are 3 zones according to the different aspect ratio of the material. The thermal diffusivity patterns of the zone is described as in Figure 14. When tau is larger than 0.022 and less than 0.075, It is the B zone. The B model is adopted. The thermal diffusivity of B zone alpha B is expressed as equation 7. When tau is less than or equal to 0.022, it is the A zone. The A model is adopted. The thermal diffusivity of A zone alpha A is expressed as in equation 8. When tau is larger than or equal to 0.075, it is the C zone. The C model is adopted. The thermal diffusivity of C zone alpha C is expressed as in equation 9. Table 3 is showing the repeatability test result for couple with different size in TDMI. The repeatability error is less than 5%. And so is the alumina shown in table 4. The repeatability error is less than 5% as well. And so is tin shown in table 5. The repeatability error is less than 5% as well. Table 6 showing the accuracy errors and analysis of the copper in TDMI test. There are 3 different A, B, C with different criteria values of the aspect ratio tau. The blue characters showing tau is in the A regions. The red characters showing tau is in B regions. The pink character showing tau is in C regions. The red font represents the accuracy error after calibrations. For example, when at test number 1 and 2, the aspect ratio tau is in B regions, the major diffusivity data does not need to be corrected because all the accuracy errors are within 10%. But for the test numbers 3, 4, and 5, when tau is in A regions, the accuracy errors could up to 47 to 50%. But after thermal diffusivity is multiplied by 2, the accuracy errors has been down to 5.12%. As to test number 11, when tau is in C regions, the accuracy error could up to 104%, but after thermal diffusivity is multiplied by 0.5, the accuracy error has been down to 2.13%. Therefore, corrected data according to different regions of alpha values or the accuracy errors in table 6 has been controlled within 10%. After that, all the calibration work, table 7 showing the accuracy errors of the alumina is within 2%. The thermal diffusivity obtained from TDMI can be expressed by equation 10 as well. In order to obtain the effective thermal conductivity, it is additionally required to measure the density of the test pieces and the specific heat. The density can be calculated by equation 11 that is measured according to the Archimedes principle. After get mass change of the water in equation 12, divided this mass change by water density, that is the volume of the test pieces. The specific heat of the test sample is measured by conservation of energy according to the first law of thermodynamics shown as in equation 13. That is, the heat absorbed by the object to be tested is equal to the heat release with the sum of the heat release of the high temperature water and the heat loss of the system. The schematic diagram of the experiment is shown in figure 15. Generally, heat loss of the system can be negative. At the beginning of the experiment, the sample with the known initial temperature and the mass is put into the container. When the heat balance is reached, the system temperature includes the sample to be tested and the water should be all the same. And both the theoretical temperature trend are shown in figure 16. the heat released by water shown in equation 14. The heat that can be absorbed by the sample to be tested can be expressed by equation 15. Since the heat released from water should be equal to the heat absorbed by the tested sample, by knowing the water mass, water heat capacity, sample mass, the specific heat of the sample is thus being calculated from equation 16, and the effective thermal diffusion conductivity case of effective of the tested pieces can be obtained. Table 8 showing the thermal diffusivity of vapor chamber A, B, C measured in TDMI. Convert the thermal diffusivity data to the thermal conductivity that is equivalent to case of VCA effective is equal to 6944, and the case of VCB effective is equal to 1000, and the case of VCC effective is 1600. Table 9 shows another thermal diffusivity of vapor chamber DEF measured in TDMI. Convert the thermal diffusivity data to the thermal conductivity that is equivalent to case of VCD is equal to 4800, case of VCE is equal to 3000, and the case of VC is 4300. The vapor chamber is not like the pure material of the copper plate. There is a standard thermal conductivity that can be found out in the table or literature. Therefore, to prove that the Angstrom theory is correct, only pierce the vapor chamber and then measure the thermal diffusivity of the copper plate. Table 10 is showing when the vapor chamber is pierced and all steam is expelled out of the chamber to make the vapor chamber is a copper plate. Measure the thermal diffusivity of these two pierced vapor chamber, get the thermal conductivity values are 370 and 380 respectively, and which is very close to the thermal conductivity 380 of pure copper material. Therefore, TDMI proved a very good thermal diffusivity and the thermal conductivity measuring tool. Conclusions. Vapor chamber is used for thermal diffusion, therefore the thermal conductivity of the vapor chamber should not be calculated by Fourier's conduction law. This paper used Angstrom theory to get the thermal diffusivity of the vapor chamber first. This study with a VC of C are in the same group with the same length and width dimension, but the different thickness. The effective thermal diffusion conductivity of VC of B thickness 0.4 mm is about the 3000th, and the effective thermal conductivity of vapor chamber C thickness 3 mm is about the 4300. It is reasonable that the thicker the thickness, the better the diffusion ability, which is consistent with the physical phenomena. Because the vapor chamber does not have a standard thermal conductivity values for comparison, the verification method for thermal conductivity values of the experimental is to pierce the vapor chamber and exhaust all the water vapor to make it an empty copper plate. Measure the thermal diffusivity of empty copper plate again, and then convert it into a thermal conductivity of 372 and 383, which is similar to the thermal conductivity of the pure copper. Hence, the data of the TDMI is very reliable. It is not difficult to use the Angstrom theory to make a measuring instrument, but the issue is that how to calibrate. This article using Angstrom theory to successfully divide the size of the current vapor chamber into 3 zones by the methods of the thickness to width aspect ratios. The repeatability errors of the obtained data is less than 5%, and the accuracy error is less than 10%. And that is all my talk. Thank you.